Hello and welcome everybody to another episode of Books and Bytes. Today, we're going to be diving deep into James Clerk Maxwell's A Treatise on Electricity and Magnetism. Now, this book from 1873, it's a bit of a beast,
Oh, he is.
but it's absolutely foundational to our understanding of, well, electricity and magnetism.
Yeah, you're not kidding about it being a beast, but it's a fascinating journey through Maxwell's mind. Essentially, he takes us through this incredible process of unifying what were once considered separate forces, electricity and magnetism. And he does it with such meticulous detail, building his arguments from the ground up.
Okay, so before we get lost in the details, can you give us the big picture? What are the main themes we'll encounter in this treatise?
Absolutely. So the first thing you'll notice is Maxwell's emphasis on precise measurement. He spends a good chunk of the book establishing a clear system of units for electromagnetic quantities. He knew that without a common language of measurement, comparing experimental results and building a coherent theory would be nearly impossible.
So it's like laying the groundwork for the entire field, making
Yeah.
sure everyone's on the same page before diving into the complex stuff.
Exactly. And from there, he takes us through a systematic exploration of electrostatics, which is the study of stationary electric charges. He covers familiar concepts like electric charge attraction repulsion and that classic inverse square law. But he goes deeper, using Faraday's concept of lines of force to visualize these invisible forces.
I remember those lines of force. They were always so helpful in understanding the direction and strength of the electric field.
Yes. But for Maxwell, they're more than just a visualization tool. They hint at something more profound, the existence of an electromagnetic field that permeates space. And that's where things get really exciting.
Okay, the electromagnetic field. I knew this was coming. That's like Maxwell's biggest contribution, right?
Absolutely. It's his revolutionary idea that space around electric charges and magnets is not empty, but filled with this invisible field that mediates the interactions between them. This field is not static. It's dynamic, changing, and evolving. And those changes, as Maxwell shows, give rise to electromagnetic waves, which include light itself.
Whoa, so light is just a ripple in this invisible field. That's mind-blowing.
It is, and Maxwell doesn't stop there. He goes on to explore how these electromagnetic principles play out in various contexts, from the behavior of electric currents and conductors to the fascinating world of electrolysis, where electricity is used to break down chemical compounds.
So he's connecting electricity, magnetism, and even chemistry in this one grand theory.
Precisely. And through it all, you see this meticulous attention to detail, this drive to unify seemingly disparate phenomena under one elegant framework. It's really remarkable.
All right, I'm hooked. Let's start from the beginning. You mentioned Maxwell's focus on measurement. What exactly does he do there?
Well, he starts by defining the fundamental units of length, time, and mass. These are the building blocks for all other units in electromagnetism. He's very careful to define these units in a way that's consistent with the existing scientific knowledge of the time, ensuring that his system is grounded in rigorous observation and experimentation.
So it's not just about picking arbitrary units. It's about creating a system that reflects the underlying reality of these forces.
Exactly. And once he has his fundamental units in place, he meticulously derives the units for other electromagnetic quantities, like electric charge, electric potential, and magnetic force. He even explores different systems of units used by scientists in different parts of the world, showing how they can be converted into each other.
It's like creating a universal language for talking about electricity and magnetism.
You got it. And it's this careful attention to detail, this emphasis on precision, that allows him to build such a robust and comprehensive theory.
Okay, so we have our units sorted out. What's next in Maxwell's journey?
From there, he dives into the world of electrostatics. He carefully defines what electric charge is, how it manifests in different materials, and how we can measure it. And then he introduces one of the most fundamental concepts in electromagnetism, Coulomb's law.
Coulomb's law. That's the one that says the force between two charges is proportional to the product of their charges and inversely proportional to the square of the distance between them, right?
That's the one. And Maxwell doesn't just present it as a formula. He walks us through experiments that demonstrate this law, showing how the force between charged objects changes as you vary their charges, and the distance between them.
So he's really grounding his theory in experimental evidence, showing us how these mathematical relationships play out in the real world.
Exactly. And it's through these experiments that he starts to develop a deeper understanding of the nature of electric forces. He introduces the concept of electric potential, which is a measure of the potential energy per unit charge at a particular point in space.
Okay, electric potential. That would always trip me up in physics class. Can you break it down for us?
Sure, imagine you have a hill. The higher you go up the hill, the more potential energy you have, right? Because gravity could pull you down and you'd gain kinetic energy. Electric potential is similar. It's like a hill in the electric field. The higher the electric potential at a point, the more potential energy a positive charge would have at that point.
Ah, that makes more sense. So a positive charge would be pulled towards a region of lower electric potential, just like a ball would roll down a hill.
Exactly. And Maxwell uses this concept of electric potential to explain a lot of interesting phenomena, like the behavior of capacitors, which are devices that store electric charge.
Okay, I'm starting to see how these concepts build on each other. But we haven't even gotten to the electromagnetic field yet.
Don't worry, we're getting there. But before we can fully appreciate the field, we need to understand the foundations that Maxwell lays out.
Fair enough. So we've talked about units, electric charge, Coulomb's law, and electric potential. What else does Maxwell cover in this early part of the treatise?
Well, he spends quite a bit of time discussing dielectrics, which are materials that don't conduct electricity well. Think of things like rubber or glass.
Right, they're insulators.
Exactly. And what Maxwell is interested in is how these dielectrics affect the electric field. He introduces the concept of electric displacement, which is a way of quantifying how the electric field is modified within a dielectric material.
Okay, electric displacement. That sounds kind of complex.
It can be a bit tricky, but essentially it has to do with how the presence of a dielectric material affects the distribution of electric field lines. Maxwell shows that when you introduce a dielectric into an electric field, the field lines become more concentrated within the dielectric, which is a key insight for understanding how capacitors work.
So the dielectric material kind of sucks in some of the electric field lines.
That's a good way to think about it. And this leads to the concept of electric susceptibility, which is a measure of how easily a dielectric material can be polarized by an electric field.
Polarized. What does that mean?
Well, in simple terms, it means that the molecules within the dielectric material align themselves with the electric field. Think of it like a bunch of tiny compasses all pointing in the same direction when you bring a magnet nearby. Except in this case, it's the electric field that's doing the aligning.
So the dielectric material becomes a bit like a mini magnet, but for electric fields.
Exactly. And this ability of dielectric materials to be polarized plays a crucial role in the behavior of capacitors and other electrical components.
Wow, this is getting really interesting. It's like peeling back the layers of an onion, revealing all these fascinating details about how electricity behaves.
That's a great analogy. And we're just getting started. Maxwell has so much more to reveal in the coming chapters.
All right, before we move on, can you remind us why all of this matters? Why should we care about these seemingly technical details?
Because this is the foundation upon which our entire understanding of electricity and magnetism is built. Maxwell's work, with its focus on precise measurement, careful experimentation, and the introduction of key concepts like electric potential and electric displacement, laid the groundwork for the technological revolution that followed.
So everything from our smartphones to the power grid that lights our cities relies on these fundamental principles that Maxwell so meticulously laid out.
Absolutely. And in the next part of our deep dive, we'll see how Maxwell takes all of these pieces and starts to put them together, leading us towards his groundbreaking theory of the electromagnetic field. Get ready for some serious, mind-blowing moments. Welcome back to our deep dive into Maxwell's treatise. So far, we've seen how Maxwell sets the stage with a rigorous system of measurement and then dives deep into the world of electrostatics, exploring concepts like electric potential and the behavior of dielectrics.
Yeah, it's been a fascinating journey so far, uncovering all these hidden details about how electric charges interact. But I'm ready for the main event. When do we get to the electromagnetic field?
Patience, my friend. Maxwell is a master builder, carefully laying each brick before revealing the grandeur of his creation. And in this next part of the book, he takes a crucial step towards that grand unification by exploring the magnetic effects of electric currents.
Okay, so we're finally moving beyond static electricity and into the realm of electromagnetism.
Exactly. This is where things start to get really interesting. Maxwell starts by describing experiments that demonstrate how a flowing electric current creates a magnetic field around it.
Ah, so that's the connection between electricity and magnetism. It's the movement of charges that creates the magnetic field.
Precisely. And Maxwell goes into great detail describing how the strength and direction of the magnetic field depend on the strength and direction of the current. He even delves into the mathematical tools used to calculate these magnetic fields. But don't worry, we won't get bogged down in those details here.
I appreciate that. But I am curious, how did scientists back then even measure these magnetic fields? It's not like they had fancy sensors like we do today.
Yeah, great question. Maxwell actually describes the instruments used in his time, including the galvanometer, which is a device that can detect and measure very small currents. By carefully observing the deflections of a galvanometer needle placed near a current-carrying wire, scientists could infer the strength and direction of the magnetic field.
It's amazing how resourceful they were back then, coming up with clever ways to measure these invisible forces.
It really is. And Maxwell, being a brilliant experimentalist himself, was a master of these techniques. He understood the importance of precise measurement and designed his experiments with incredible care.
So we've got electric currents creating magnetic fields. But what about the reverse? Can magnetic fields create electric currents?
Ah, you're anticipating Faraday's law of induction. And yes, Maxwell dedicates a significant portion of the book to exploring this fascinating phenomenon. He describes how a changing magnetic field can induce an electromotive force in a nearby conductor, which in turn drives an electric current.
We have a changing magnetic field. So it's not just the presence of a magnetic field, but how it changes over time that matters.
Exactly. It's the variation in the magnetic field, either its strength or direction, that induces the current. And this is the principle behind electric generators, which convert mechanical energy into electrical energy by moving magnets near coils of wire. It's one of the most fundamental and important applications of electromagnetism.
Wow. So every time I switch on a light, I'm witnessing Faraday's law in action. That's pretty cool.
It is. And Maxwell, building on Faraday's work, takes this concept even further. He starts to explore the idea that electric and magnetic fields are not just separate entities that influence each other, but are actually two aspects of the same fundamental phenomenon. He begins to develop the concept of the electromagnetic field, a unified field that encompasses both electric and magnetic forces.
Okay, we're getting closer to the big reveal, but before we dive into the electromagnetic field, I want to go back to something you mentioned earlier. Electrolysis. How does that fit into all of this?
That's a great question. Electrolysis might seem like a separate topic, but Maxwell uses it as another example of how electricity and magnetism are deeply intertwined. He explores how electric currents can be used to decompose chemical compounds, separating them into their constituent elements.
Right. I remember learning about this in chemistry class. You pass an electric current through a solution, and it breaks down the molecules.
Exactly. And what Maxwell emphasizes is that this process involves the movement of charged particles within the solution, which are essentially electric currents at a microscopic level. He connects this to the concept of electrochemical equivalents, which are the amounts of different substances that are deposited or liberated at the electrodes during electrolysis for a given amount of electrical charge.
So he's showing that even chemical reactions are governed by the laws of electricity and magnetism.
Precisely. It's all part of his grand vision to unify these seemingly disparate phenomena under one theoretical umbrella. And this brings us to a crucial turning point in the book. Maxwell starts to challenge the prevailing notion of action at a distance.
Action at a distance. What does that mean?
Well, before Maxwell, the accepted view was that electric and magnetic forces acted instantaneously across empty space. One charge mysteriously influencing another with nothing in between. Kind of spooky if you think about it.
Yeah, it does seem a bit magical. So how did Maxwell challenge that idea?
He argued that the key to understanding these forces is the concept of the electromagnetic field. He envisioned the field as a medium through which these forces propagate not instantaneously, but at a finite speed. And that speed, as he later calculated, turned out to be the speed of light.
Whoa, hold on a second. Are you saying that Maxwell's theory implied that light itself is an electromagnetic wave?
You got it. It was a revolutionary insight, and it all stemmed from his rejection of action at a distance and his insistence on understanding how these forces are transmitted through the field.
This is absolutely mind-blowing. So all those seemingly disparate phenomena, electricity, magnetism, light, are actually different manifestations of the same fundamental force.
That's the beauty of Maxwell's work. He weaves together these seemingly separate threads into a magnificent tapestry, revealing the interconnectedness of the universe at a fundamental level. And in the next part of our deep dive, we'll explore the mathematical machinery that he developed to describe this electromagnetic field culminating in those famous equations that revolutionized physics.
I can't wait. This is turning into a real thriller. Welcome back to our deep dive into Maxwell's treatise.
I'm still reeling from that last revelation, the idea that light is just a ripple in the electromagnetic field.
It is a profound insight, isn't it? And it's just one of the many treasures that Maxwell reveals in his masterpiece.
So we've seen how Maxwell carefully laid the foundation for his theory, from defining units to exploring electrostatics, and then made that incredible leap to connect electricity, magnetism, and light.
And now in the final part of his journey, he gives us the tools to describe this unified force in all its mathematical glory, Maxwell's equations.
Okay, here we go. I know these equations are a big deal, but honestly, they always seem kind of intimidating. Can you help us demystify them a bit? Absolutely. Remember, equations are just a language, a way to express relationships and patterns in a concise and precise way. And what Maxwell's equations do is capture the essence of electromagnetism in four elegant statements.
4 equations to rule them all, eh?
You could say that. And believe it or not, they're not as scary as they might seem. Let's take them one by one. The first one is Gauss's law for electricity. It tells us that the electric field emanating from a charge is proportional to the amount of charge.
So the more charge you have, the stronger the electric field it creates.
Exactly. Think of it like a light bulb. A brighter bulb emits more light, right? Similarly, a larger charge creates a stronger electric field, and this field spreads out in space, just like light from the bulb.
Okay, that makes sense. What about the second equation?
The second one is Gauss's law for magnetism. And it's a bit of a curious one. It essentially tells us that there are no magnetic charges in isolation. You can't have a north pole without a south pole.
So unlike electric charges that can exist on their own magnets, always come in pairs.
Exactly. Magnetic field lines always form closed loops, unlike electric field lines that can start from a positive charge and end on a negative charge.
Interesting. So no magnetic monopoles lurking out there in the universe. What about equation number 3?
That's Faraday's law of induction, the one that explains how changing magnetic fields create electric currents. It's the principle behind generators and transformers, which are essential for our modern electrical grid.
Right, we talked about that earlier. It's like magic. Moving a magnet near a wire creates electricity.
It does feel a bit magical, doesn't it? But it's the elegant dance of electric and magnetic fields interacting with each other.
Okay, last but not least, what does the 4th equation tell us?
The fourth one is Ampere's law with Maxwell's addition. It describes how electric currents create magnetic fields. But Maxwell added a crucial piece to the puzzle. He showed that changing electric fields also create magnetic fields.
Wait, so it's not just moving charges, but also changing electric fields that generate magnetism.
You got it. And it's this addition that completes the picture of the dynamic interplay between electricity and magnetism.
So it's like a feedback loop. Changing electric fields create magnetic fields, which in turn can create electric fields, and so on.
Precisely. And it's this feedback loop that allows for the existence of electromagnetic waves, those self-propagating ripples of energy that travel through space at the speed of light.
This is mind-blowing. It's like Maxwell opened a window into a whole new realm of the universe, revealing the secrets of light and electromagnetism.
And the beauty of it is that these four equations encapsulate it all. They're not just abstract mathematical symbols, they represent a profound understanding of the forces that shape our world.
It's amazing to think that Maxwell's treatise laid the foundation for so much of modern physics and technology.
Absolutely. And it all started with his relentless curiosity, his meticulous experimentation, and his brilliant ability to synthesize diverse ideas into a coherent and elegant theory.
So what would you say is the most important takeaway for our listeners?
I think it's this. The world is full of hidden connections and patterns. And by carefully observing, questioning, and experimenting, we can uncover those connections and gain a deeper understanding of the universe around us.
That's a powerful message. It reminds us that there's always more to learn and explore, and that even seemingly complex topics like electromagnetism can be made accessible with a little bit of guidance and a lot of curiosity.
And who knows, maybe some of our listeners inspired by Maxwell's work will go on to make their own groundbreaking discoveries.
That's a great thought to end on. Thank you so much for taking us on this incredible journey through Maxwell's A Treatise on Electricity and Magnetism. Until next time, keep those minds curious.